So number 17. Number 17?
Or 20, sorry.
Okay.
I had it written as 17.
Okay. Okay. Well, the stress strain curve, it does a bunch of funny stuff, but before it does funny stuff, you have the linear elastic region, you know. This is the linear elastic region. And the slope of the graph in there is E. So you calculated E from,
yeah.
And so you could, so that's all I wanted you to do is just, draw that thing and say like the slope is,
okay.
Yeah. I just want you to notice that relationship. So whatever whatever you got for the Young's modulus, just put it in there as the slope, and then that's the answer to this question. Any other questions about anything, any homework problems? Okay. Man, I'm trying to figure out what I want to do here because I printed out the next thing we're going to do for notes and just noticed that. So I think I'm going to just talk about, I'm going to talk about the next topic that we need for homework, and I might have to make some corrections later. We'll see. But the next thing we need to talk about, so remember what the last thing was that we talked about? We talked about members in pure tension or compression and coming up with the stresses for those. Another case of bodies that are in pure tension or compression is pressure vessels. And really, for our purposes, it's going to be pure tension because we're going to imagine that these vessels, instead of trying to keep high pressure from compressing them, is going to have the high pressure on the inside and be trying to resist like explosion, And we're going to have two cases. The first one is spherical pressure vessels. And the second one is cylindrical, pill shape. Yeah, except so we're going to have so in both cases, we're going to have an outer pressure, let's call that P outer, okay, and an inner pressure, P inner. P outer, and then remember that this pressure is always applying forces perpendicularly to the surface. So this is P inner. And what I'm going to call the pressure P is P inner minus P outer. Okay, so a positive value of P means P inner is greater than P outer. Okay, so this is shaving cream canister, not a oxygen tank, not a submersible, you know. Okay, so let's start with spherical pressure vessels. And instead of thinking about the P outer and the P inner, we're just going to think about this net pressure P. And let's think of 1/2 of the sphere. Okay. So there's part of the sphere that goes up here, but we're not isolating that in our free body diagram. Okay. And we have this force that's being applied to the part that we're isolating. That's acting this way. And what's applying that force F? So F is the force applied to like our chosen half by what's applying that force. That's the force being applied by the material that we're just ignoring for this analysis. Okay, so that's being applied by, like if that's made out of metal, that's being applied by the adjacent metal. So let's just call this the adjacent material. Okay, and what is that force being applied to counteract? It's being applied to counteract a pushing force from the pressure acting all in here. Okay.
Is that pushing force like coming out from the center of the sphere?
The pushing force is, so imagine this thing full of some kind of fluid, you know. This is, so remember that pressure applies forces perpendicular to any surface. Okay, so our surface, we've cut off, so we're analyzing the material, but we're analyzing the metal or whatever that the sphere is made out of. But we're also analyzing that half of the water inside or the gas inside. So the red is the force that's being applied to the gas that we're including in our chosen half by the gas that we're omitting.
Should there be arrows like pushing laterally?
Yes, but those all cancel out. Because of the symmetry of the shape. You know, like, yes, there would be an arrow fate going that way, but there would be an equal and opposite arrow going that way. Because that's the way pressure works.
What about like pressure pushing against the sides of the sphere?
Right, well, you're right that those are there, but there's one going this way and one going this way. And so if we're doing a Newton's second law analysis of the whole thing, then those are gonna be equal and opposite pairs and disappear.
So at the boundary, there's only the perpendicular arrows.
If you're doing Newton's second law for a full thing, yeah, everything cancels except this stuff that I've shown.
Okay, I think I get it.
Well, yeah. Okay, so think about what now that I think about it, I don't think, those aren't there, the things that you're talking about, and it has to do with what we're isolating, okay? If we were isolating the spherical shell, then yes, the pressure would be applied. If we're only isolating the metal shell, then those pressures are going to be pushing out on the sides, But we're not isolating the metal shell. We're isolating the filled metal shell, okay? And so the forces that are pushing out like that, the metal is also pushing back on it. So those are actually Newton's third law pairs. And this is all the forces that are acting on it. There's nothing else going on. Yeah?
Why would you include this stuff in the middle instead of just the shell?
Because you'll see that we get a really nice result out of analyzing it this way.
Okay.
I mean, you can analyze whatever you want. Like we could analyze a quarter size shape here and then the shape of a giraffe or whatever, but then it would be a mess and we wouldn't get anything good out of it. But we're gonna get something nice and simple out of analyzing the deviled egg shape, Yeah.
I'm just a little confused on the forces on the shell part. So is that the pulling force of like the other half of
Yes.
the shell trying to hold the shell?
Trying to hold it together, that's right.
Okay,
Yep.
and the pushing forces on the gas or liquid is just the properties of that gas or liquid
Right.
wanting to expand and fill the container?
Yeah, so any kind of pressure is always pushing on everything. And so the gas that we didn't include that's in that light blue, the light blue half is pushing down on the gas that's in this half.
Okay.
The gas that's in this half is also pushing up on that, but we don't care because of what we chose to isolate.
Okay.
Yep. Okay. So the red force is the pressure times the area in there. And that is the pressure force that's applied to the material in the bottom half. Let me call that the chosen half. By the, and instead of material, let me change this to fluid. because this has to be some kind of gas or liquid inside. So fluid in the chosen half by the fluid in the other half. Okay, so assume that the walls are relatively thin. So assume that the walls of this spherical vessel are thin. Compared to the radius. And the radius is r. And the thickness of the walls is lowercase t. Okay. Well, then PA is equal to that net pressure times pi r squared. And that force is going to be equal to the area in the perimeter, you know, the area in the material, times the normal stress. So this is going to be the normal stress times the area of the, let's call it like the rim. Okay, so what's the area of that rim going to be? If you imagine taking that thin-walled circular shape and breaking it at one point and stretching it out, you can think of it as a long rectangle. So this is going to be sigma times the perimeter is 2 pi r times the thickness. And now for this to be in static equilibrium, Newton's second law says that these two have to be equal. And so sigma is equal to the pressure times R over 2T.
And what was sigma again?
Okay, so let me draw what that is. So this is going to be a normal stress. Okay, so this is a normal stress in the walls. And this is in any direction tangent to the wall. So if this is your spherical vessel, and you have your x-axis going this way, and your y-axis this way, and your z-axis perpendicular. then what you have is that your XX normal stress and your YY normal stress are both equal to PR over 2T. And your ZZ is 0. And all of your shears are 0. Question?
Yeah, so is the radius here to the like inside wall or is that outside wall?
We're going to assume that, yeah, we're going to assume that the thickness is small enough that that it doesn't matter. That making that distinction is kind of like being overly confident in the precision of our calculations.
Okay, so if we see the phrase like assume that the thickness is small in relation to the radius, that's kind of the key. It's like
Yes.
it doesn't really matter.
That's right. Yep, that's right. And also, so if as the thickness of the walls gets bigger compared to the radius, you start getting, for one thing, you start getting different stresses at different points along the thickness, okay? And for another thing, you start getting shear stresses. But the thinner it is, the more you approach this limit of having nothing but normal stresses in the plane of the vessel.
Okay.
Yep.
Can you explain the shape you drew?
This?
Yeah, like why do we have like it looks like a slide stick in it?
Yeah, I don't know what I was trying to do there. I was just trying to give you a sense of what the sphere looked like.
So it's just a point on the surface of
Yeah.
It's giving the sphere shape.
Yeah. This only works for oranges.
Basketballs?
Yeah, I guess beach balls and basketballs possibly too.
Spheres are hard to draw on the
Yeah, I know. Yeah, it's hard to get it across convincingly, but the key thing is that this z-axis is perpendicular to the surface, normal to the surface.
Kyle, I understand the approximation we're making with the area of the rim, but why didn't we just find it by taking like the area of this difference of the circles? Like if you know the thickness of the wall,
That's what I was wondering.
so why not?
Yeah, why not?
Like when we did the washers,
Uh-huh.
you know, in the
Yeah.
statics.
I mean, my guess is just that you get something ugly, but I don't know what you would get, but so you would get like so you would have this area of the outer thing would be pi r squared. The area of the rim well, let's just do the area of the inner, would be pi r minus t squared, which would be pi times r squared minus 2rt plus t squared. And so the area of the rim would be pi r squared minus pi r squared, that part's good, plus 2 pi r t minus pi t squared. Those cancel, and 2 pi r t minus pi t squared And so you get, so depending on how big t is, this goes away because you're squaring 2. So, okay, so you get that instead. And then, yeah, it looks like you just get something uglier.
Okay.
But if that t is small, then
It's basically
Then it
negligible.
limits
That's
to it.
What you had originally.
yeah, in the case that t is small.
Yeah.
Do we use this approximation anywhere else, like an area of rim equals 2 pi RG?
Yeah, we use that approximation all the time in coming up with infinitesimal, like for integral definitions and stuff. That's a pretty classic. Yeah, if you have a.
It's familiar.
Yeah, right.
There's something here to do with physics too, like that.
Yeah, you see that all the time in calculus derivations. Anytime you're, so anytime you're, so you always have to define your infinitesimal element when you're doing an integral definition, and anytime you're deriving those as, like, in statics, we did it when we were,
The bearings.
that's right, that's what it was.
Yeah.
Yeah, so, we were doing this integral definition, and this distance was r, and this was dr. And so because this was infinitesimal, the thickness of this thing, you could take this rim, separate it, stretch it out, and just the area in there is just the perimeter times the thickness.
So if you try to stretch out a non-infinitesimal.
Yes, correct.
What,
There.
do you get like your missing area is like?
Yeah. I don't know if you have extra or if you're missing, but yes, then it's not an accurate calculation for a finite thickness circular ring, I guess. Well, that's what we saw here. That's the difference, is that extra term pi t squared.
Yeah.
Okay, what are we talking about? The principal stress tensor for these things is pi r over 2t, not pi p r over 2t for y, 0, 0, 0. And so the max shear stress is p r over 2t minus 0 divided by 2, so p r over 4t. All right, so for example, if you have a spherical pressure vessel with a radius of 0.1 meters and a thickness of 1 millimeter. And the pressure on the outside is atmospheric pressure. So 1.01 times 10 to the 5th pascals. And the pressure on the inside is, let's say, 5 times that pressure, so 5.05 times 10 to the 5. And we want to calculate the maximum shear stress. The XX and YY stress are P times radius over 2T. P is the inner minus the outer. So 4.04 times 10 to the 5 pascals. And so we get 4.04 times 10 to the 5 times the radius of 10 centimeters, 0.1 meters, divided by 2 times the thickness of 1 millimeter. And you get 4.04 times 10 to the 5 times 1, 2. And you get principal stress of 2.02 times 10 to the 7 pascals. Well, that's XX and YY normal stresses, so the maximum shear stress is half that, so 1.01 times 10 to the 7 pascals.
Is there regionally similar to the mountains, where the stress is sharing, where you get, where like the P in and P outer are equal, and then like the outer stress is bigger than P in?
Yeah, so the problem is, in theory, this should work for, this should work perfectly fine, whether P outer is higher or P inner is higher. But the problem is that if you put this thing into compression instead of tension, it's not going to fail in the same way that it fails here. Instead, it's going to buckle at some point, and this can't account for buckling. So if no point of this thing ever buckled in, and this thing just compressed until it just purely failed in compression, and it never changed from being a sphere, it just got to be a slightly smaller sphere as it compressed, then this would work perfectly. But long before that happens, little tiny imperfections in this thing are going to cause a spot to buckle, and that's where the failure is going to happen. And so that's why the numbers that you would get out of that aren't useful. Yep.
So the max shear stress, is that also just in the two orthogonal directions tangent to the surface?
So that, so remember, once you have that principal stress tensor, And so like this is the principal stress,
Mhm.
this is the principal coordinate system, okay? And you have the principal stresses corresponding to that. You have two normal stresses that are equal to this and one that's equal to 0. So whichever one you choose to be the middle, the middle stress is going to be one of these two. So you're going to rotate 45 degrees about either the x or the y axis.
Oh,
Rotate the coordinate system, and then that's going to show you where where that shear stress is going to happen. So yeah, you could think through the geometry that way. I mean, so this is the only thing that's new, and then the rest is just interpreting, principal stresses and stuff like we're used to doing in other cases.
yeah.
Uh, all right. So the other type of pressure vessel is cylindrical. This is applicable for a lot of things like tubing or blood vessels or anything like that. So we're going to assume that the what would I say? So like, let me draw a picture. So we can separate this into the end pieces and the middle piece. And we're going to assume, like if we call this L, and these end pieces have a radius R, let's not use R. Let's call that little L. We're going to assume that L is a lot bigger than little l. And we're going to use a coordinate system where x is along that long axis, y is also in the plane of the surface, and z is normal to the surface. Okay, well, we're going to think about this two different ways. Again, we're going to do everything by chopping stuff in halves. So let's first think about this half. Okay, and just like before, we have this force resisting the pressure force. Okay. So the black is the force F. And F is the force applied to the rim of the chosen piece by the adjacent material. And the red is the pressure times the area, and that is the force applied to the chosen fluid by the adjacent fluid. Okay, well, thinking about it this way, so R is going to be the, the radius of this cross section, and everything is going to work out exactly like it did in the circular case, as you can imagine. So in this direction, it works just like the spherical vessel. So you have the XX stress times the area, which was 2 pi r. That is the length, and then multiplied by t, the thickness. Is equal to the pressure. That's not funny.
Yes, it is.
Pi r squared. That cancels. That cancels. The pi's cancel. And you get that in the x direction, sigma is equal to p r over 2t. That's just what we got before. But the y stress is going to be different.
I was like, in this direction. What about the other?
Yeah. So, so the y direction is different. So in that case, we're going to ignore the stuff that happens at the ends. Okay, it's like a peanut butter filled celery. Um, And then counteracting that is the pressure from the fluid. The meanings of these are the same as they were before. Okay, so let's calculate these forces. So this force F is the YY stress times the total area of material that's resisting this pressure force. And so the total area here, if this thing has a length of L, okay, what would that area be? 2 times, because there's 2 sides, the thickness times L. And the pressure force would be, so pressure times area is the pressure times the area is 2 times the radius. You see that the width of that is 2r times the length. Newton's second law says 2 YY TL is equal to 2 PRL. The L's cancel, so that doesn't matter. The 2's cancel, and you get that sigma YY is equal to pressure times radius divided by T. Yeah. And so in this case, your principal stress is PR over 2T, PR over T,
C direction just always gets going down.
what?
So the C direction just always gets going down.
Yeah, it does. Well, that's how we set it up. Too bad. So tau max then is PR over T minus 0 over 2, so PR over 2T. So the maximum shear stress is twice as big as in the cylindrical case. Twice as big as spherical case. Okay, any questions? These kind of problems are really just plugging numbers in, and you won't have to do very many of them.
How come we're not looking at like the